Alright, hi everyone, welcome to my YouTube channel, City of Electrons. So in this video we'll talk about electromagnetic wave equations. Electromagnetic wave equations. Note that this is the guy we are talking about. Wave. Let's say you throw something, okay, and I like to use water because it's something you can easily see the wave, okay, because wave can be seen and unseen. You can see it, and there are waves you can see, okay. And of course the wave we are talking about now are the ones we can't really see: electric wave and waves of electric field and waves of magnetic field. But at some point I'll use water to illustrate, so it will be easy for us to physically picture in our mind. So now when we say wave equation, what do we even need them for? Okay, the thing is this: what we need wave, look at this. Wave moves from that. I should have left that thing, no, but it's okay. Let me just use this. Okay, now this wave moves from one point to another. I know it's like going up and down, but the thing is, it moves from, let me zoom in, moves from this point to another point. Yes, it's continuous. Yes, it is continuous, but it moves from one point to another, like it's traveling. Okay, it's being propagated. So how is wave propagated, or how does wave travel? Okay, now this is where we need an equation to describe how wave travels. The equation will help us to describe how wave travels. So how does waves of electric field, how does it travel? That's electric field wave for electric field. Then how does magnetic field wave, how does waves of magnetic field travel? That's wave for magnetic field. Okay, so that means we'll have two equations here. So when we say electromagnetic wave equations, they are just equations like this. Is an equation that describes how wave travels through space and time. Of course, this wave goes through space and it takes time. Are we seeing it? It travels through space and it takes time. Okay, so yeah, and it takes time. Now we derive the wave equation using differential forms, being that differential forms describe what's happening at a point. Remember, I just explained that waves move from one point to another. So when we talk about points, each point, different points, it's simply we have to talk about the differential form, using differential form. Just like saying the bush caught fire. Yeah, the bush caught fire. So when you say, okay, how did this happen? Okay, you start from a point, and then this is happening in this camp, and then from, let me just use, let's say this is a tree, this is a tree and another tree, different trees like that, funny trees. Now if this place caught fire, and let's say the fire began from somewhere here, okay, now when describing how the whole place caught fire, you say, okay, it started from here, and then it went to this part, and then went to this part, and then went to this part. Okay, so it's moving from one point to another, and the Maxwell's equation that describe in terms of points, individual points, of course, that is the differential form of Maxwell's equation. So in deriving our wave equation, we are going to make use of the differential form. Okay, we are going to make use of the differential form. So we already have the differential form. Okay, we already have the differential form. But note that, so we are making use of the differential form. I think I've said that, yeah, making use of the differential form. Okay, now no need for that. Now, since we are making use of the differential form, that's one thing. But in order to know how this wave truly behave? Are we listening? In order to know how the wave truly behaves, we need to remove everything and see the true nature of the wave. Okay? See the true nature of how wave is being propagated. If we have some, if wave is being propagated through space and time, of course, through space and time, and there are other factors affecting it, we can't really tell the true behavior of the wave. Are we saying it? Yes, you can see how the wave behave, but since it's affected by other things, you can't really tell the exact behavior. What if the things affecting the wave change to another things? Okay, so in order to get the true nature of the wave, what we do is this: we consider free space. Free space. So what we have there is just the wave. I know it sounds somehow, but just to get the true nature of the wave, we consider free space. And in free space, there is no charge. Okay, no like charge density. So let's put that here. So considering free space. Okay, so the wave equation we are about to derive now is for what? Free space. Okay, for free space. Are we ready, or are we together? We are ready and together. Okay, so let's go. So I just said that in free space, thus charge density, let me do that here. The charge density, which is rho, equals what? 0, because we are considering free space now. So the charge density is 0. Take all these guys out. Okay, now also the current is what? There's no charge now, so the current is what? 0. Are we together? Both charge density and current is 0. Now having these two, let us write out the Maxwell's equation. Okay, let us write Maxwell's equation. So for the first one, which is Gauss's law, for Gauss's law we have what? And just Gauss's law. Okay, so for Gauss's law we have this for the electric field equals what? Note, okay, let me just write the whole thing first. We have this, isn't it? We have this for Gauss's law. But since we are considering free space, okay, since we are considering free space, what are we going to have? This will be what? This will give us what? This will give us 0. Is that not so? Rho is 0 now. Is 0. So that means we will have it as what? We will have it as this. Equals what? 0. So in free space, this is Gauss's law. This is what Gauss's law turns out to be in free space. Okay? Then the second one is what? Let's see. The second one is Gauss's law of magnetism. Okay, so in this case now, is that, I think I will bring this icon down, okay, so that at least when everything is aligned. Hope we are following. And please, as you follow up with pen and paper, okay, that will help a lot. That will help you a lot. Okay, yeah, better. Okay, so for Gauss's law of magnetism, we have it as what? Pam equals what? 0. Please, we've done all this in the video, in the previous videos. Okay, Gauss's law usually is 0. Gauss's law for magnetism, that's the divergence of the magnetic field or the magnetic flux equals what? 0. So already we have this as 0. So yeah, that's that. Okay, third law. Okay, Faraday's law of what? Induction, sorry. induction. Okay. And for Faraday's law of induction, what do we have? We have that the coil of the electric field, okay, negative of what? The magnetic flux. Okay, this is what we have for Faraday's law. And now look at it. Is there anything that will make anything zero? There's no I here, so it remains. There is no it remains. Okay, so we're good. We're good with that. We're good with that. Okay, then the fourth law, which is what? Ampere's Maxwell's law. So Ampere's Maxwell's law. So in this law is on what? Magnetic. Okay, and of course we have this enclosed. All this formula we've done them in the previous video, so you can just watch that and see what's going on. Okay, done them in previous videos. Okay, and then rho, epsilon naught, which is permittivity, and then we have this partial E, partial T. Good. Now looking at Ampere's Maxwell's law, okay, looking at this law, you can see that being that we are talking about free space, the charge is what? Zero. Charge is zero. So what we have here should be zero. Zero multiply this thing, everything here is gone. Okay, so what we have left here will be what? Rho, permeability, which is a mu naught, epsilon naught, which is permittivity, and then we have this, and we have this. Write this in well. So these are the laws we are going to make use of. These are the equations we are going to make use of to derive what? The equation, the wave equation. For what? Free space. Free space. Are we together? So since we've gotten the law, now next is to derive the equations for free space. The one for a magnetic field and the one for electric field. Now, so out of these four laws, which one can we use for to derive the wave equation for electric field in free space? Note, if you are talking about electric field, look at it now. This or this. So these are the two, electric. Okay, if you are looking for the magnetic, this is where you have this or this. Now let's start with the electric. Okay, let's start with the electric. For electric field, for the wave equation for electric field in free space. Okay, so already the two equations that has electric field, this one is zero already, so we can't do anything with it. So just allow the guy, leave the guy. So what we'll do, we'll come to Faraday's law, because this is your other one that has an electric field, and this guy is not equal to zero. So let's go with this. Okay, so I think I should just copy that over to save time. So we'll go with this, copy, and then voila. Now I didn't name this thing, or I didn't. Okay, but it's okay. So since we have this now, the next thing for us to do, let's just call this equation 1. So as we make our solving easy, equation 1, then call this equation 2, and then call this equation 3. You know what? Let's just, oh, sorry about that. Give me a minute, just a second. Will do. Those are the equations, the equations we're making use of. Call this one equation 1. Let's go with that, okay? It's a useful equation here. So the next thing to do is to what? Take the coil. Take the what? Take the coil and the coil of both sides. Both sides of equation 1. Do I have to write all this? Equation 1. Okay? Take the coil of, I'll make that smaller later. Take the coil of both sides of equation 1. I'll tell you why we take the coil. It's just a simple idea. You can give me your own idea in the comment section. Please do. Thank you. So why are we taking the coil of both sides of equation 1? Because if we do that, this is coil now. We'll now have this. Are you seeing it now? This is this coil now. Coil, look at it. We are now taking another coil, taking the coil of both sides, meaning we'll have this equals negative coil of this. Are you seeing what's going on? Can you see what's happening? Equation 2. Okay? So of course this I missed this. Nabla cross. Okay, I see what's happening. Now, this Nabla cross, that's coil now. So when we say take the coil of both sides, we mean Nabla cross should be here, Nabla cross should be at this other side of the equal to sign. And of course, we already have one Nabla cross here. So this will now have Nabla cross, which is coil of the electric field. Okay, equals this. Are we seeing what's happening? Now, there is one identity, one vector identity. This is it. And the identity states that if you have the coil, look at this. Let me put a short statement there. Using the vector identity, which is this. If you have the coil of a vector, let me use V of a vector. Okay, if you have the coil of a vector, that is the same thing as saying it's equal to the gradient of the divergence of the vector minus the Nabla square. Nabla square, that's what? Laplacian, okay, of the same vector. Now, if you prove this thing, like if you expand this, the value you will get, is exactly the same if you expand this. But well guys, I'll tell you the truth, the expansion is really, well, it's really like serious expansion. Okay, it will take you a lot of pages. So instead, just memorize this. Okay, just memorize this, put this somewhere. Okay, now have you seen that by taking, once you've seen this, like you have one coil here, if I take another coil, it will result to this expression, which you can just simply take what? This. That is, we can now say, instead of writing this whole part now, we are going to write this. Meaning, we'll have, for our left hand side, we'll have what? Nabla and this dot. In this case, what's our vector field? E. So let's go with that. E. Are we following? Minus what? The Laplacian, which is just simply Nabla squared. Why am I still using V? Before I continue, can we see what's going on? This identity, it matches with the identity. That means this whole thing is equal to what? This whole thing. So where you see V, you plug in E. So E will be here. E will be here. That's why we have all this here. Are we following? That's our left hand side. Please let me know in the comment section if there's anything confusing, please. Okay, so it's, let me just even put, to simplify further, let me even make it like very obvious. So let me bring these guys here, bring this guy here, bring this guy here. Okay, make it very obvious. Are you seeing it? You see this thing? That's exactly what we have here now. Is that not so? And we said there's an identity, which means if you have something like this, it's equal to this. You can memorize that. Okay, just do that. Now, where you see V, you put E. Clear? Where you see V, you put E. Where you see V, you put E. Is that clear? Okay, hope that's clear enough. So now we return everything. Okay. So, and already this guy is equal to this guy. Is that not so? So we can now say equal to what? Minus this all over this T. Bracket, brethren, nabla cross B. What is this? Look up. What is that? Can you see it? Exactly. Okay, this one, exactly. Are we seeing it? So therefore you can copy this or substitute this. Substitute that. For me, I'll copy it. Copy that. And then where you have that, you just plug it here. Plug. Simple. Okay? And we see what's going on. Good. Also, this guy dot, come up here, come up thither. Can we see it? Look at it here. And that's what? 0. So you come down here and you say what? And you say what? Nabla cross 0 minus this. Of course, that means everything here is what? Gone. So we just clean this guy. So we just clean this guy out. And we have this left. I hope we are following. It's clear now, B? Let me know in the comment section. Okay, now, so what we have to do is just to expand this guy now. This multiply this and multiply and so on. So what will happen there will be what? Negative mu naught epsilon naught, and then what? When this multiply this, you get what? Squared now. So that will be squared all over this T squared, and voila. Woo! That's it. So of course the minus sign will obviously cancel out. It will cancel out obviously. Piao, piao. So what you have left to be what? This guy equals, let me just say, okay, I can leave that there. Okay, which will also result in what? Result in, you can just say that will be, you just bring this guy over and you have this. What an E. Okay, and you have this. So this will be the answer. So this is the answer for that electric field now. Okay, so we've gotten this part. Then the next part is to get for the magnetic field. Note that this is the wave equation for electric field in free space. In free space. So for, what equation is this now? So let's call this one equation 3. Okay. Whichever, the number of equation doesn't really mean, okay, you can call that equation whatever, as long as you can recall and make reference to it. So the next one now is for magnetic field. So the wave equation for magnetic field in free space, to get that we need an equation from Maxwell that has the magnetic field, either the flux, magnetic flux or something, but something magnetic. Now This one has magnetic flux, but it equals 0, so we can't make use of it, so we leave that. The other equation that has magnetic flux is this. Okay, so we're going to take this from Ampere Maxwell's law. Let me just copy and I'll edit it there. Copy these parts. Okay, so copy, so good. Now, but we don't need this stop. Don't need this stop. Don't need that. Okay. So from Ampere's Maxwell's law. Okay, from Ampere's Maxwell's law, what we'll do next is this. What we'll do next is this. Taking the I think I don't need to write that because it's the same step, the same process with the first one. The same process with the first one. That is what you take the coil of both sides. I've already explained why we did that. Why? That will make our simplification easy because it will lead to this vector identity. Okay, so let's just go with that. It will lead to this vector identity. So I'll just write straight mainly for the statements. Now, when you take the coil of both sides, what's going to happen here? You will have the coil. You will have the coil of magnetic flux, that's of B, and then this. Note that the coil affects the field. Okay, affects the vector field. Affects the vector field. So yeah, are you seeing that the coil these guys are constants, so the coil just goes straight to affect the vector field, not the constants. Okay, so of course, using that vector identity, this will give us what? This part will give us this, okay, minus this squared. Okay, then this other part, this everything here. Please let me know in the comment section if you are following and if everything is okay. Just let me know. Now, okay, let me write this down first. It's just the same thing. Now, what happens next? What is this? Okay, divergence of B, that's the magnetic field. Come back to this. That's what? 0. Okay, so we'll come down here and we'll put what? 0 there. And once we put 0 here, everything here is what? Is gone. What we have left here will just be what? Minus Laplacian of this. Okay, then for this, look at this. Are you seeing this expression? Nabla cross the electric field, which is the coil of the electric field. We'll come back here, we'll see we have exactly that here. Wow, very correct. So we'll just pick this. I think I should just copy it to be on the safe side. Okay, we just pick this and then we'll go. Now let me just drop it here. Okay, already I have to write all these ones first, so that will be this partial. Now all this guy comes in. Okay, all over this T. Okay, so what's going to happen next? We just simplify and simplify. So this will be negative this equals, when you open the brackets, you open this bracket, this negative sign will come out, and that will give you what? Negative mu naught epsilon naught, and then squared, okay, all over this squared. Done. Now looking at this, I didn't even name this equation. What? Equation 4. Please, I know I didn't mention, like, I didn't give numbers to all the equations, but you can just do that when solving along. But you know, the main thing is that you understand the equations, you understand how to derive the equations, and how to make reference to what equation. If I had given numbers to all this equation, I would have said substitute equation 2 or equation this into equation that. Are we getting it? Okay, so maybe I should have given like equation 1, 2, 3 and so on. So this is just it. So with this, we have gotten the wave equation for electric field in free space, that's equation 4. Then the wave equation for magnetic field in free space. Oh, I think I should have simplified further like I did. Let's do that now. Let's simplify further. Okay, let's simplify further before we call it equation 4. Now, of course, we see minus in both sides. That will give us that. They will cancel out. Okay, cancels out, and that leaves us with nabla squared, which is the Laplacian, equals this. Okay, all over this. And of course, when you just bring that over to this side, it gives you this, gives you this, gives you this, equals 0. Equation 4. Better. Now, looking at this, brethren, if you look at these equations, the one for electric field in free space, wave equation for electric field in free space, and the wave equation for magnetic field in free space, look at them carefully. The only difference is that for this, the vector field is E, labeled E. So also here, the vector field here is B. The rest things are the same. Are we saying it? Okay, so just take note of that. Okay, now, okay, I think we'll just leave this, we'll stop at this point. Okay, in the next video, look at this. Okay, we'll talk about something here. What do we mean by that? See you in the next video. Okay, so like, share, subscribe, and I'll see you in the next video. Thanks for watching. Bye for now.